Okay, great. Is my mic on? Can you hear me? Awesome. All right, hello, welcome. This is kind of dark, but I can see you all very well, so this is good. Like Mark was saying, my name is Steffani. I'm a fourth-year PhD student in the department here at the University of Toronto now. So I'm almost there, nearing the end. But I'm really excited to be telling you a lot about a really quite fascinating field of astronomy tonight. And I'm going to try to make it really interactive. So hopefully that's good with everyone, but we won't be like just listening to talking for a lot. We'll be kind of doing a bit of a back and forth. But like Mark was saying, tonight the title of the talk is The Past, Present, and Future of Milky Way Globular Star Clusters. So we'll be talking all about that now. Okay, so first of all, maybe like a quick show of hands. When there's no power outages and no clouds, who likes looking up at the sky and seeing stars? We are at an AstroTour, so like, yeah, that's expected. Who gets sad when you look up in Toronto and you see that's what the night sky looks like? Yeah, like it's not the best place for stargazing, right? Toronto's a huge city. There's tons of light pollution, as pretty as the skyline is. Unfortunately, not the best for astronomy, right? But if you've ever been fortunate enough to just kind of go up a couple hours north, this is a time lapse taken in Algonquin Park. Maybe many of you were out there for the fall colors recently. But you see here the sky looks totally different, right? Over the course of the night, you see tons of stars. They're kind of, some are flying across the sky. You see the Milky Way kind of projected all across the sky like that. And there's a lot more to see than just looking up in Toronto. So this is kind of the first part of where this talk becomes interactive, because I really wanted to get a sense of what everyone knew about this talk already. So if you have a phone with you, what you can do is you can pull it out, and you can either scan the QR code, or you can go to this menti.com and enter this code right here. And what it's going to do, what I'm asking you here is like where you think the stars in the night sky come from. There's so many there, but where did they actually originate? So I'm going to pull this up. We should have a word cloud here starting as soon as people start putting responses in. Okay, one person, Big Bang. Okay, we'll give it maybe like a minute so you all have a chance. And if you missed the code, it's just at the top of the screen there. Okay, we got some good ones. British Columbia, I'm liking that one. Okay. Pressure, gases. The programmer, perhaps later we'll talk about that. That's kind of true. Aliens, no. No, sorry, spoiler. Okay, a lot of people are saying Big Bang here. We got space, gas, hydrogen, Milky Way. There's really a lot of good answers here. Okay, maybe let's do like 20 more seconds just to see what we kind of get to here. Guess, okay, yeah. All right, okay, it's kind of slowing down, so maybe we can stop for now. But there's a couple answers there that are actually pretty close to what we're going to be talking about today. Big Bang is a good one. It's kind of how everything started. We're not going to be talking too much about cosmology. I'm sure a future AstroTour will get into that. But don't worry, there's more of these polls. We can have fun with this all night if we want to. So we'll go back to this for now. But what I would say is, if I could just say one sentence on where the stars in the sky come from, is that almost every star once belonged to a star cluster. So people were saying gas and hydrogen and Big Bang, and that really is all true, right? Like that is how the universe started, with this Big Bang. You know, like hydrogen is important. There's gas in stars. We know this. But the place they started is really these star clusters, which is the focus of the talk tonight. Okay, so let's jump into the past and figure out, you know, we know where these stars come from, but let's talk about it a bit more. So looking way back in time here, this is kind of a classical picture in astronomy. All the way on the right here, you have the present day. So this is, you know, things that are going on right now. There's lots of stuff in space, right? There's planets, asteroids, like tons of stars, galaxies, etc. That's kind of in the present day. And then, as many people said, you can go all the way back 14 billion years ago to the Big Bang. And this is how we think the universe started. And there's these objects called star clusters that when the universe was really, really young, so about 11 to 12 billions of years ago, these objects started to form. So I think these are really, really cool because when you look up at the night sky, these star clusters, in particular these globular clusters we'll talk a lot about tonight, are really some of the oldest objects you can actually take a telescope, point it up in space, and see. They're super, super old and can tell us a lot about, how even we got here today. Okay, so we know stars came from clusters, but how do you actually form a star cluster? See, we're kind of doing the little pieces of the puzzle here. Well, someone said gas, and that was a really great answer because in space a long time ago there were tons of what we call giant molecular clouds. And this is kind of exactly what you'd think of in what the name describes here. First of all, they're giant, they're really big. Molecular is just they're made of molecules, mostly hydrogen, and then they're clouds, so giant molecular clouds. And these clouds are really held together by something called hydrostatic equilibrium, which is a really giant and confusing word, and all it means is that the inwards force of gravity that wants to collapse that cloud is balanced by the outwards pressure force that the cloud exerts outwards. So these clouds can just exist for a while in space, and they can hang out and just chill and do their thing. But what happens is these clouds can, pretty picture first. These clouds are very pretty to look at. This is an image with the Hubble Space Telescope. I like this one because it was just Halloween and it's kind of spooky. It's giving me a little bit of a ghost vibe. I don't know, with the black dust and the orange. I think it's really nice. But again, you can see lots of dust, right? There's kind of patches where the stars are blocked out, and this giant gas cloud in the middle. So it's really nice to look at. But if you've been following along with space news, as I'm sure many of you have been, you'll see that the James Webb Space Telescope, or JWST, has been just doing a wild amount of observing lately on many different objects. So this cloud here looks totally different, right, than the other one we just saw. Of course, people put colors and things like that. Don't worry about that too much, but this is just kind of another way that you could visualize what this looks like from real observations. Okay, so going back to this cloud, like I was saying before we looked at the photos here, what can happen sometimes is that in space, far away, some stars will explode, and when a star explodes all the way over here, material and waves can travel all the way over here to where this giant molecular cloud is hanging out, and it kind of disturbs the cloud. So I've said that it's in this equilibrium, right? There's this balance, it's very stable, but when these other external influences kind of cause this cloud to be disrupted, what happens is that the cloud collapses. So you have this giant kind of spherical cloud that gets really, really small and it starts collapsing. And when it does that, two really important things happen. And that's that the pressure and temperature of the cloud increase. So things are getting really, really hot. And when things are getting really, really hot, you can kind of imagine what happens next, right? If you have this hot gas, things are getting hotter and hotter, you're going to eventually get protostars, which are really tiny little baby stars that are almost hot enough to be called stars, but eventually they turn into stars. And because these clouds are so big, you can get tens, hundreds, 10,000s, and even millions of these stars in one place. So you could say, this is maybe a bit of an older reference, but a star cluster is born. All right, okay, I'm glad. I wasn't sure to include it, but I'm glad there are a few Star is Born fans in the audience there. Okay, great. Okay, moving on. Star clusters are unique. I think this is a really fun part of this area of astronomy because they are so different. Even when you go home tonight, you can look up different pictures of star clusters. They're so beautiful. I love my job because I just feel like I get to look at pretty pictures all day. But they look so different, and I'll show you a few examples of them right now. So the first kind of wimpy type of star cluster, I'd say, is not even really a cluster. It's more of an association of stars. So these are called stellar associations. They're groups of about 10 to hundreds of stars. So you could kind of say that's a cluster-ish, they're stars kind of nearby. But it's super low density regions. They just kind of hang out. But what's crazy about this is that about 70% of all the stars in our universe, we believe, came from these stellar associations. So you look at this and you say, that's not very exciting, that's just a group of 10 stars. But really, this is where most stars in the night sky, when you look up, in Algonquin Park and see that whole time lapse of the Milky Way, most things came from here. And this includes maybe my favorite star, which is the sun. That's actually quite an active area of astronomy right now, is trying to find the stellar association that our sun once belonged to. Of course, we don't live in a star cluster right now, but at some point, it is very much believed that we did. And trying to find out, where we started from is pretty active research, and you'll see a bit later in the talk how we can kind of try to do that, which is pretty cool. Okay, so moving on, we get to things called open clusters. And now you're getting a bit bigger here, right? These are groups of about, still on the low end, tens, but thousands of stars. This is a very beautiful image, I think. Does anyone know what cluster this is? You can see it. Look up. You can just yell it out if you know. What did you say? Pleiades, yes. This is actually one of my favorite star clusters, and maybe some of you have seen it and not even known. But on a clear night, you can look up, you'll see a group. It actually starts rising in December. You can see it from December to February, so make sure you try to do this. You look up and you see 7 stars that are close together. This is the Pleiades cluster. It's an open cluster, it's small, but it's still very interesting for a lot of reasons. But today what we're going to be focusing on are these globular clusters, right? You are just getting to absolutely wild amounts of stars here, tens of thousands to millions of stars, super high density regions here. And even when you compare these 3 images, you see that they look really, really different, right? And you can say here, if I just wanted to kind of order them by age, these stellar associations are very young. You kind of go up here, and like we were just talking about, globular clusters are very, very old. Okay. So this is what we're focusing on today. And what's cool about this picture is it's very, very dense, right? There's a lot of stars in this image. And you can ask yourself, we of course don't live in a globular cluster, but if we did, what would our night sky look like? It would look very different than what it looks like. I'll start by saying that. This is a simulation done by actually local astronomers here at the University of Toronto and at McMaster, so that's kind of a local connection. But what you're looking at here is if we lived in this cluster core, which is that really dense, bright region in the center, this is what our night sky would look like. So right now, if you look up, super dark sky preserve, you can see about 1,000 stars-ish in the night sky. If you lived in a globular cluster, you would see about 130 in the night sky. It would be a lot. And it would be so bright, it would actually be about 20 times brighter when we have a full moon. So I don't know, good luck getting some sleep, maybe, if you're like me. I probably wouldn't want to live in a cluster core, but I don't know. All right, what if we go about halfway out here? So on the right, you can see, you can start to see this kind of cluster on the right-hand side and maybe a bit of an influence from a galaxy on the left side. The sky is super, super bright. If you keep going out all the way to the cluster's edge, you again see this beautiful kind of like jewel box of stars. Galaxies. It would look really, really beautiful. But yeah, this is kind of what things would look like, just to put it in perspective when you're looking at the night sky right now. Okay, that was the past. That was how we get these clusters. But what are they doing today? That is going to be the next portion of this talk. Okay, so right now, the best estimate for how many of these clusters in the Milky Way is about 159. You can imagine how many stars that is just in clusters, right? 159 times a million is a lot of zeros. I don't really know how to say that. I'm not going to pretend to know the number of what that is right now. But there's a lot of stars in our galaxy are isolated in these clusters. And the thing is they're not just sitting in the sky, right? These clusters are moving and they're doing really, really interesting things. So what you're looking at here is an image from the Gaia Space Telescope. I'm sure if you attended Henry Lung's Astro tour a couple months ago, he showed you this image. But if not, what you're looking at here is every point is a star. And this is real data. I think it's one of the best images that's ever been taken in astronomy. You can see our galaxy in the middle. You see there's dust. You see there's blobs of light that are kind of like very interesting stars. You see that there's tons of light coming from the center. It's so beautiful. It's about 1.5 or just over a billion stars. So it's really quite amazing. But this is just stars, right? You can kind of isolate where these clusters would be. And if I kind of just throw those clusters on there already, what you see is you can kind of ignore the red points for now. Don't worry about those. But each blue point and each blue point's line represents a globular cluster and how it's moving through the galaxy. So what you can see here is these clusters are really quite active, right? They're not just staying in one spot in space. They're really moving across the sky, which is really cool because interesting things start to happen. Okay, here's a movie. Again, ignore the red trajectories and just focus on the blue. But if the spiral galaxy represents our Milky Way, each blue kind of wraparound you see is an orbit of a cluster, and you just really see just like how chaotic this could be, even with just 159 clusters. They're really going all over the galaxy here. And as these clusters orbit the galaxy, they change. They don't just stay the same. And what can really happen is stars can be stripped or pulled away. And what happens here is that you have stars in this like big kind of sphere, right? They're traveling around the galaxy, but the galaxy is huge, right? And we know big things give a lot of gravity. They have a high gravitational force. So when they're orbiting around the galaxy, stars can get pulled away. And this is what you're seeing in this image here. This is a real simulation. This is a super active area of research at U of T. Each of these kind of blobs represents a globular cluster at varying distances from the center of the galaxy. And you see that after each one kind of goes around, it's no longer spherical, right? They're getting kind of stretched out into what are called stellar streams or tidal tails. And you see that these clusters totally change their shape. Stars leave, stars go in interesting positions. But really, these clusters are not really clusters anymore. They're kind of streams across the sky. And it gets even more complicated. Stars are just, it's chaos inside a globular cluster. They're not just going around the galaxy, but stars in the globular cluster are going around each other too. So on the left here, this is a real image taken with the Hubble Space Telescope. Each dot is a star. You can see it's very beautiful. And then on the right here is a simulation. So this isn't real. This is done on a computer. But each point shows you a star, and each line shows you the star's movement in the cluster. So you can see as you get to the cluster center, it's just white. Like you can't even separate any individual stars. It's just a lot is going on. And you can visualize this with a movie here. Of what's actually happening. This is again a simulation. We could never travel to a globular cluster and observe it and film it, and this is what we'd see. We simply would never get that data as much as I'd love it. So what we do is we simulate it. Each point is a star, and how big the points are represents just how big the star is. Bigger points are bigger stars. And there's a couple things happening here. You see that these big stars are kind of like getting big and then they disappear. So these are stars exploding. There's smaller stars where even if you just pick one and follow its orbit and like what it's doing, you see it gets close to another star and then it gets like flung away. Or there's like kind of two stars near each other and then they come close and then they get flung away. It's just, yeah, it's very chaotic. And there's a lot of different ways that stars can actually interact with each other in clusters, and the type of ways they interact are really important for how a cluster changes over time. So first of all here, maybe the most basic scenario is something called a two-body encounter. There's two bodies, each body is a star. One star comes close to another star, and that's the interaction. This is really important because it's really essential for that tidal stripping and those stellar streams we just saw. Because when they get close to each other, The big star will sink to the center of the cluster at the core, and the small one will travel to the cluster outskirts. So now imagine if you have all of these really tiny stars at the outskirts of your cluster and this giant Milky Way, those are very easily going to be pulled away, and you're going to get the streams that we just saw. So that's super important for that. But then you can also have other things. This is my favorite one. It's called a three-body encounter. You again have that single star, but now you introduce another system here that's not just one star, but it's a binary system. And what this means is you have two stars and they're orbiting each other. So you can kind of treat it as one object in this case. Now, here's a simulation again of what's happening here. You'll see a single star going in, and then there's the binary, and it just gets flung out, okay? That single star leaves. Maybe it wasn't a big enough kick. It kind of comes back, okay? It can still kind of hang out in the cluster. But then eventually it'll get so close, the interaction will cause this single star to get a super high kick and leave the cluster. Wild. Crazier things can happen. Four-body encounters, two binaries. I don't have a simulation for you here. This is like still very complicated to model, but you could imagine, two binary systems. If the three-body was powerful enough to like kick that star away, then this is like that, like times 10. It's very, very high speeds. But for this talk, like I said, this is my favorite one. And these are relatively common in star clusters. Relatively common for me means it happens once every 10 million years. But in astronomy, that's pretty short. So yeah, that's like for reference. Astronomers, you don't deal with real numbers. This is, All right. So what you're looking at now, we're focusing in on that three-body interaction. You see a star at the center here. This is a cluster. This is one cluster. And the dotted line represents that star's orbit throughout the galaxy, okay? So that's what we just saw. And then every colored point that is coming out here represents one of those single stars that you just saw getting flung out of the cluster. And you see that a lot of things happen, right? These stars that aren't moving that fast kind of stay near the cluster, right? But you're getting some stars, you're traveling at about speeds of 200 kilometers a second that are just totally leaving that cluster. I made this simulation as part of my thesis, and I think it's a really pretty color palette, so I'm excited to share it with you. But yeah, this is really, you could imagine when there's lots of stars, these really can just travel all over the galaxy. And that's what we're showing you here. So imagine you have this tidal stripping, right, that can just strip these low mass stars, you get these stellar streams, okay? So the cluster's changing like that. But then they're also doing dynamics in the cluster, right? They're moving around so chaotically, these interactions are happening, they're getting flung out all over the place. So what happens is these stars get dispersed all throughout the galaxy. Yeah. That's hard. These stars can really travel around the galaxy. They can tell you how a cluster formed, what will happen to a cluster, how will it eventually die. But they're really hard to trace back. So my next question for you here is just thinking about things. If a star leaves a cluster and now it's on the other side of the galaxy or a distance away, how do you actually find what its parent cluster was if it's in the field? So I'll give you about a minute to think about that one. I'll open up this poll. Okay. Okay. Cool. Air tag, I'm liking that one. I wish I could do that. That would be good. I like ancestry DNA. That would be expensive for 1 million stars. Let's see. I also ask it nicely. So true. What if we just did that? This one's fun. It's not as obvious as the other one, right? We all settled on that Big Bang gas. I'm liking trajectory. I'm really liking composition. Whoever's saying that, that's you should have my job and be up here and talk. Maybe I'll give you 20 more seconds. Okay, I like this. I would like to end on aliens part 2. Once again, no. Whoever keeps saying that, it's just like, we need to have an aliens AstroTours talk, apparently. Okay, so really good guesses. I'm really liking trajectory, composition, elements, location. Those are all really great. Okay, so let's see what the answer is. Here we go. Cluster stars are made of the same elements. Whoever said that, round of applause, good job. And they move the same. So whoever said motion, nice. Okay, we can break this down a bit more. Returning to this spooky giant molecular cloud. All right. The chemistry of the stars in this, of all the stars that make up this cloud and the resulting star cluster that forms from this cloud should be the same as the cloud. It kind of makes sense, right? Like if this cloud is sitting in space, it's made of the same material. So that gas, when it collapses, it's not really like changing too much. It'll make stars, but they should all be kind of made of the same thing. And now this is just a reminder of how chemistry works and how you can tell chemical elements of stars. When you look up on a clear day, wouldn't it have been nice if that was today, hey? The telescopes could have come out. Oh well, you can see a picture of it now. You see the sun, right? It looks white, okay? Light usually appears white. But what happens here is if you shine it through a prism, classic picture, maybe someone's favorite album in the room, I don't know, light becomes separated into different colors. So even though we see it as white, it's not white. It's made up of a whole spectrum of different colors, right? And one of my favorite images in astronomy is this. It kind of looks like a rainbow, right? And what this is showing you here is all the light from the sun. And just at different wavelengths, that's kind of what the numbers are there. We don't really need to talk about that too much. But what's kind of interesting about this is it's not just like giant filled out blocks, right? You see that there's kind of these black lines. These are called absorption lines. What does that mean? When the sun emits photons, or any star really, they're emitting them from the core of the star, okay? And as they kind of get sent from the core, they interact with all the gas on the outside of the star. This is really to say that like stars, like they have layers, right? So like classic ogres are like onions, but like kind of stars are too, I guess. You could think of them like that. But the takeaway message here really is that each absorption line you see represents a chemical element that was present in that star, okay? So if we go back to this, that's a lot of absorption lines, that's a lot of elements, right? Stars contain a ton of elements, a ton of different elements in them. So we've kind of covered that bit, but stars that form from a cloud should also be moving in the same way, okay? And the thing here is that, you know, when a star escapes, it should have a similar chemistry to that of the parent cluster, and it should be moving the same, like, you know, to the parent cluster. But how do you actually, like, combine all this information, right? You're dealing with, like, dozens and dozens of different types of data. So I'll give you a little analogy here. Suppose you wanted to, you know, all these dogs, right? Like, everyone loves dogs. Here, I'll show you the picture. You know, like there's 12 different dogs here, and you want to find out, you know, and kind of classify and separate the dogs based on one trait, size, okay? So this could be like, for stars, like one element, hydrogen or like oxygen or whatever. It's not that hard. Copy and paste, there you go. Small, medium, and large. It's not that hard to do when there's 12. What happens when you have hundreds of dogs? How do you classify these? I'm sure my advisors were happy. I spent 20 minutes copying and pasting and sorting those. It took a while, but you're able to still classify them and do that, right? You're only looking at one trait. But it gets more complicated, right? Like, what if you want to, like, size isn't the only thing that distinguishes those dogs from each other, right? You have hair length, personality, ear style, tail length, eye color, like there's so many more things, right? And there's a prof at U of T who really says it best here, who said, you know, humans don't have like high dimensional eyeballs. We can only see in 3 dimensions, right? So how do you actually recognize patterns like this? It's hard, and especially when you're dealing with dozens of elements and dozens of, you know, motions and things like that, it becomes really hard to do this. So maybe quickly I'll give 30 seconds here, and we can I'll ask you, how do we find escape stars of clusters with lots of data? So you have all of this data. We know that chemistry is important. We know that motions are important. But how do we actually combine this together? And I will keep this one kind of short because I think I only have like 8 to 9 minutes left. Who said UMAP? You should be up here. Okay. ChatGPT, so true. So true. Ask Google, yeah. Light reflection, okay. Machine learning, okay. Okay. Okay, so I'm not gonna keep, hey Siri, so true. All right, so I'm really liking this machine learning, which is where I kind of want to talk about, like, kind of end the talk on here. Correct, yay, whoever said that. These images, I put machine learning into like an AI image generator, and this is what it gave me. So some machine learning is truly better than others, is what we've all learned today. That's sometimes, okay. Okay, how do you do this? How do you use machine learning to trace these stars back to clusters, okay? So the first step here, it makes sense that if you want to find stars that are a part of a cluster, you should really know what stars are in that cluster already, so you have something to compare it to, right? What you're looking at here is a figure of cluster stars in blue. All of these stars belong to the cluster, and you're looking at it in something called a right ascension and declination space. This is essentially astronomical latitude and longitude. The only difference here is instead of it being on the Earth, it's on what's known as a celestial sphere, and it's just a way to find stars and mark their positions in space. So you could think of it as just like a position diagram. All right, so every star in blue here, you see that they're very bunched together, they're very close, they belong to the cluster, cool. This pink circle here is what's known as the tidal radius of the cluster. This is the boundary in space where anything within that tidal radius will be gravitationally bound to the cluster. It'll be like stuck to it, right? And then anything that escapes that can be like go off and like do its thing in the Milky Way. It won't be attached to the cluster anymore. So any star that was once in the cluster that then, gets stripped or does a 3-body encounter or something like that and goes beyond the tidal radius becomes known as an extra-tidal star. Okay, so we already said, now that we kind of have the stars in the cluster, we want to find stars that have similar chemistry to those stars using machine learning, right? This is what we've kind of led up to. All right, this is a result of the machine learning. Okay, I've told you this, I labeled that wrong. Okay, you can kind of flip those axes, that's okay. Basically what this means is that you've given this 19 different chemical elements. We cannot see in 19 dimensions. What this algorithm does, someone said UMAP, that's what it's called if you're interested, is it projects it down to a 2-dimensional space that we can see. We read in 2 dimensions. We look at things in 2 dimensions, right? So what this means is that any point that is close to another point has similar chemistry in all 19 elements. That's what that means. So it's good that those stars that we saw before that were close to the cluster are clumped in this machine learning space, right? Because it means that their chemistry is similar too, as it should be. These stars are not part of the cluster. You see that they're very different than those ones in blue. They have some other kind of chemistry going on that we don't need to get into today. But you'll see that there's all of these gray points, right, that are near these blue ones. These stars are made of the same chemistry. That's all it means. They're similar to the other ones. So what you've done now is you found chemically similar extra-tidal candidates. These are stars in the field that were not close to the cluster that share chemistry. But the thing is we also said motions were important, right? We've only looked at chemistry up till this point. So this is where now you can simulate stars escaping a cluster and compare them and their motions to the stars that you just found that were chemically similar, okay? So we return to our favorite 3-body encounter. And what we do is for one cluster here, we can simulate where all of these stars would be. We can simulate what their motions would be, what they would look like, where they would end up. And we can compare that to the stars that we just found that had the similar chemistry. And really, again, going back to this point, this allows us to find the stars that are chemically similar through like 19 different elements and also move the same as the cluster stars. And when you do that, hooray, yay, we find some extra-tidal stars that we think belong to the cluster. We find 10 of them, actually. You see that they're beyond that tidal radius. That means they're kind of off farther away in the galaxy. This made me really happy. It was a year and a half of my PhD. I kind of felt like that once they accepted my paper. So all is good, right? All is good. Or is it? Ooh. So what's fun about that is we did find like 10 of these stars that had escaped from a cluster, right? That's great. We can learn how one cluster evolved. But I just told you at the beginning of the talk, there's 159 of these clusters in the Milky Way, which is like, come on, like I don't have 159 times a year and a half to like finish my thesis. Like that would be too long. Sad. Unless our new goal was big, but it was to find these stars from every globular cluster, okay? And this is where the title of the talk comes in. 2 weeks ago, I finished this project called A Catalog of Galactic GEMS. No, we're not talking about crystals, sadly, today. But we are talking about globular cluster, extra-tidal mock stars. Yay. Astronomers have like really bad acronyms for things. This was maybe my attempt at coming up with one, but it's kind of cute, so it works. What are we doing here? You have these three-body encounters again, right? We're simulating how these stars move and where they're going and where they'll be across the sky. So there you go. I do this simulation, and I don't just do it for one cluster, but I do it for 159 of them. And it turns out that these GEMS, or these globular cluster extra-tidal mock stars, can really be found almost everywhere in the Milky Way. So this is a simulation. And what you're seeing here is, I think the contrast might be a bit bad for some of these, but you see that you can really, again, it's that position diagram. These can be like dispersed all throughout the galaxy. Like each of these kind of axes here represents the whole sky. And you're seeing that you're getting some that are kind of like blobs, you're getting some streams, some kind of look like donuts, that one's kind of cute. Like there's like, they're doing a whole bunch of different things. They look different, right? These stars can be everywhere. And you can kind of group them by, the clusters themselves. Like where are the clusters located in the galaxy, and how does that change what the stars or these extra-tidal star distributions look like, right? These are the clusters that are close by. You can see that for the most part, you kind of have that one purple kind of like stream coming out, but most of them are kind of little blobs, right? If you're interested, this is the galactic center, which is why everything is so concentrated in that one region. But when you go out, a lot of these are really, really streamy. They look totally different. So it shows you that, where this cluster is in the galaxy, even though these stars are kind of being ejected in chaotic ways, they can form really interesting distributions across the sky. And if you combine this whole picture together, this is all the globular clusters in the Milky Way, you truly see that they can be everywhere, where each color here represents stars of a given globular cluster. There's 159 points on there. But for the most part, these stars kind of do follow unique paths, which is great because you can use this catalog and combine these simulations with real data to find new extra-tidal stars. Cool animation of us combining our data with real stars. This is ongoing work. There's a couple of really awesome students at U of T that are working on this, undergrads. So if there's any undergrads in the audience, you can get involved in research. It's very fun. You get to learn about cool things. And this is kind of where I'm going to end today because we still need to do all of this machine learning and chemical identification. Like it's not done yet, but we have a really great simulated catalog of where to start. And again, when you find these stars, right, they tell you how these clusters evolve, how they formed, how they'll die, what that means for our galaxy. And the galaxy is really our home, right? So the more we understand about these like really like big like cosmic environments that are just doing crazy things, we kind of get to understand more about us, right? And maybe, I know I am a bit over time, but I do want to give you one more poll because people seem to really be into the polls. Do we want one more poll? Yeah, okay. Because now you're all star cluster experts. Even like some of the answers here today were really impressive. So my question to end it is to you, what do you think we should explore about star clusters in the future? maybe you'll inspire a new project. I don't know. Yeah. That's it. I'm closing the poll. That's the only one. No, alien again. Oh my God. Okay. It's just, yeah. If aliens created them, extragalactic interaction. Okay, fancy alien. Okay, there are some actual good ones here. So, like, you know, I do like to hear about, like, black holes and positions and things like that. That's really great. But maybe I'll end it here, and you can see how the word cloud evolves as we have 7 minutes for questions. So thank you, everyone. That's it for today.
Okay, thank you so much to Steffani for that really wonderful and interactive talk. It's very clear that our next talk should be on alien life, so we'll try to
should, yeah.
We'll find some expert who, we'll find an expert on aliens. Yeah, so we're now happy to take any questions before we start heading over to AV. Any questions for Steffani? And Steffani, you can pick.
Sure, I saw it in the red shirt.
Repeat the question.
Yeah, I'm assuming that only stars that are thrown out of clusters tend to get planets. Like if you were in a cluster, I think it might be hard to form planets.
That's a really, okay, so the question here was, is it, to paraphrase, is it only clusters that, is it only stars that leave a cluster that can form planets, or can you get stars and clusters that also form planets? The answer is, it's actually easier in a cluster to get those planets. And that's because when you basically form these stars, right, you can kind of think of everything spinning. So there's like this cloud of gas, but the cloud of gas doesn't just go like shloop, but it goes like, and it spins. And these over-densities, like these regions where there's more gas in one region than another, are what form these stars in the first place. And then in these really heavy regions, there's material spinning around the star, and that's where you would get planets. So it's kind of like during this whole process of that big cloud collapsing and forming that star, that's when you're also forming the planets. That was a study that actually is being worked on at U of T right now too, so that was a really great question. But yeah, it's mostly in a cluster.
Yeah, I have sort of a follow-up one.
Okay.
Is there any difference between stars that get thrown out of clusters and stars that remain in clusters?
Is there any difference? That's a good question.
What type of star that gets thrown out? Right.
So it depends how it gets thrown out, right? If it's something like the tides, right? Like the galaxy pulling them away, they'll probably be the same, more or less. What can happen is like those 3-body encounters where you have the binary and the star. If something gets really close, there's gravity from both of those things, right? So what happens is sometimes you can kind of be like stretched, or like weird things happen like that, and some of one star can kind of get like transferred to the other star and things like that. So that can change things as they leave clusters. But yeah, it's truly so complicated what goes on inside this. But that was a great question, yeah. Yes?
Not to disappoint the people, are there aliens? Are the stars long-lived enough and to generate planets in the habitable zone so that life could evolve and be stable in there? And if you were in a globular cluster for science fiction reasons, obviously,
yeah.
You would be able to move from star to star within human lifetimes, wouldn't you?
That's it. Okay, so I guess there were 2 parts to that question. One was, can you get, just paraphrasing, like can you get habitable planets? And
you know, can you get a planet with enough length of life so you can
sure.
get intelligent life, and then could they
can you get intelligent life in those clusters as the first part there? I mean, it's kind of like it's unanswered, right? It's like whether you look at a star or a planet in a cluster versus a star or a planet like that's just kind of in the field. We don't know. Like, we really don't know. Of course, nothing has been really found at this point, so I can't really comment on that. But these are really dense regions, but you could still think of, even though that I showed like it's chaotic and there's a lot of stars, they're still decently far apart. Like it's not like they're running into each other and colliding super often. So jumping from one star to another star would you'd still need a lot of fuel to do that. It's not like they're like little neighbors, but yeah, good question. Okay, I saw your question, you've had your hand up.
With this, are you expecting to find the origin of our sun?
Oh.
So, how will it help?
Yeah, so the question was, with this, are you expecting to find the origin of our sun? And if so, how would it help? I look at globular clusters and open clusters, so those two that were a bit older. I don't look at stellar associations. My advisor did my PhD advisor did a really similar kind of thing where you could do that machine learning and look at the chemistry, and then look at chemistry at different regions in space and compare that to the sun and see if you could kind of backtrace the sun with that chemistry and line it up with different clusters. They didn't find anything, unfortunately, right now, of course, right? But yeah, this method of chemistry comparison and things like that can totally, you could trace things back, but unfortunately the cluster that our sun came from has probably dissolved, it doesn't exist anymore. It was so small that it just would have kind of dispersed and all the stars are in space. So it's, how do you trace something back to something that doesn't exist, Tricky. Yeah.
We have time for maybe one or two more questions.
Cool. Mark, go ahead.
No,
you go, please.
No,
please, Mark. I insist.
I can.
Okay, yes, right here.
Are there any globular clusters that are passing by a known black hole?
Ooh, that's a good question. Some of these globular clusters have black holes in them, which is pretty wild. They're not super big. Of course, the center of our galaxy has a really supermassive black hole that is just giant. Most galaxies have that. But there are smaller black holes inside these clusters. So the clusters orbit the galaxy, and if that's at the center, maybe you could say that kind of it does. It doesn't really interact too much, but these black holes and clusters can do a lot of the same stuff we talked about today and eject these stars. Imagine a star gets close to that and just totally they're not going 200 kilometers a second, they're going thousands of kilometers a second. They're called hypervelocity stars. They're all over the Milky Way. It's really just never ending, this subject, but that was a good question. I will stick around too for a bit if people have questions and we didn't get to them, so happy to talk more.
We can maybe take one more.
Sure, yes.
If